Our next talk is recorded, but the speaker is online, and so we'll be able to answer questions. It's Christopher Zapart, and the talk is Julia Meets Big Data, JVO Experience with Distributed Computing.
Hi, I'm Christopher Zapart from JVO at NowJ, and well, today let's talk about Julia. Today's talk is not only about Julia, it's also about big data. Now, for the purposes of this presentation, let us define big data as datasets that cannot be processed by a single computer. Basically, we are talking distributed storage, distributed computing. Well, we just need a supercomputer. Now, SKA guys, please do look away. The largest publicly available ALMA FITS file is only about 350 gigabytes. So we are nowhere near SKA's 256 terabytes of data. But then again, ALMA 2 is on the horizon. Such big datasets almost invariably require remote viewing. There's just no way anyone can download terabytes of data to their own computer within a reasonable timescale. As most of you might have been aware, at JVO we have been offering a way to preview FITS files in a web browser for, well, quite some time, occasionally presenting our work at ADAS. And there is also the new kit on the blog, the new Carta Viewer, which is really like a Swiss Army knife. And now, after churning through very many different programming languages, we at JVO have been busy working on a distributed supercomputer edition of FITS Webgl coded in Julia. But before going ahead and talking about Julia, here are a few words about the one major difference between our FITS Webgl and the new Carta Viewer. Well, basically, when you view a 3D FITS data cube via FITS Webgl, you're presented with a single 2D image built up based on all the frequency channels present in the data cube. This means a lot of work on the FITS Webgl part, since we need to go through the entire dataset at least once. If it's 1 terabyte of data, we go through 1 terabyte of data. Carta, on the other hand, may seem faster on large datasets, and this is for a good reason. They do not read all the data. Carta only shows you one 2D image corresponding to a single frequency channel. So even for 1 terabyte large FITS files, they only show you one small part of the big picture. This is the main difference. Carta, less work but no overview. FITS Webgl, we do more work so that you can see the big picture. We have finally come to the Julia part. Well, guess what? Paul Barrett has already introduced everyone to Julia. Thank you, Paul. So here's my take on the subject. Julia is typically positioned as a faster and better alternative to Python. Just like Python, it is interpreted. But here's where the similarities end. Unlike Python, out of the box, Julia gets compiled down to the machine code like C or Fortran. Well, personally, I think of Julia as Foltran on steroids, and this is for very good reasons. To start with, arrays begin at 1, like in Foltran or Wolfram Mathematica. You've got vectors and matrices working out of the box, and you can broadcast a scalar function across a matrix, just like in modern Foltran. But unlike Foltran, you can also do low-level systems programming in Julia. There are mutexes and spin locks, hash tables, web development tools, and most importantly of all, strings just work. Foltran is infamous for having multiple string implementations that never quite seem to work properly. Well, does Julia actually work? Well, see for yourself. So here we are, a supercomputer edition of FITS Webgl, and there is a Julia logo, so yes, we are running on Julia, and we are using a small cluster comprising of 4 desktop computers. So let's open about 80 gigabytes of data. There you are, and the real-time spectrum display is quite smooth, no problems here, and we can show you data frequency channel by channel as well as streaming video. So now here comes the big test. Let's open 350 gigabytes of FITS data. and here we go. It's all in RAM, and the action is quite smooth, as you can see. So the question is, why do we have such large data sets? Well, the answer is that each individual frequency channel, well, it corresponds to a 2D image about 11,000 pixels by 11,000 pixels, and there are 700 such large frequency channels. So this is the reason why we've got about 350 gigabytes of data. So here we are looking at some major scientific programming languages. At JVO, Rust has been working great in the production environment for the last 3 years. However, when it came to trying it out in a small cluster, I have run into some serious problems with the various messaging libraries, for example, ZeroMQ, or especially problems with the nanomessage library. So switching over to C++, well, yes, you can actually write memory-safe programs in C++ in a Rust manner. You just end up with a spaghetti code full of lambdas and smart pointers everywhere. Seriously though, C++ feels much slower compared with pure C. And I have had some problems with the ever-changing new WebSockets networking library as well. Plus, there are no native matrix variables available in C++. So in comes modern Foltran 2018. CoArray Fortran to be exact. Well, Foltran is not bad at all. As you well know, Foltran has been used on supercomputers for many decades. It is still in use in NASA, and it does its work very well. The newer editions, like CoArrays, make it easy to do distributed computing on clusters. Unfortunately, CoArrays are not concurrent. They are not asynchronous. So you cannot serve requests coming from multiple users at the same time. There's more on that on the next slide. So finally, we have turned to Julia for help. I first used Julia about 3 years ago, but it was quite unstable at the time. 3 years is a long time. Right now, Julia has got very stable, and most importantly, it's got fully asynchronous distributed computing. Plus, it offers a very productive development environment as well. So these are the main reasons why I have finally settled on Julia. Here's a slide about some shortcomings of CoArray Fortran. Well, basically all requests have to be processed sequentially. So you can only handle request number 2 after finishing the previous request number 1. Request-response pairs must match precisely. This isn't a problem in a scientific computing application. But when you look at a typical web application, requests come all over the place at different times. And whilst some requests can be handled in a short amount of time, the others take longer. So you no longer have a first-come, first-served situation. Instead, you may get last-come, first-served. The CoArray Fortran simply gets confused. You will get incorrect results. As a countermeasure, all request-response pairs needs to be serialized, implying a large performance hit. This is one thing that everyone wants to know. How fast is Julia in real-life usage, not in synthetic benchmarks? Julia folks have been making some extraordinary claims about beating Foltran. In my experience, at best you could get about 100% the speed of C or Foltran. But in casual use, for example, hash tables, string concatenations, HTTP WebSocket responses, well, typically you would get about half the speed of C or Foltran. One thing is certain, the development times are shorter. You simply get more productive in Julia, just as you do in Python. Let me give you a gaming analogy. I guess nobody would play an Xbox game at 30 frames per second. 60 FPS is the bare minimum. But what about 120 FPS? If 60 FPS is deemed sufficient, well, you may not necessarily need 120 FPS. At some point, running at half the speed of C or Foltran simply becomes sufficient, good enough. You may not even notice an extra delay of 1 millisecond or so. What are the reasons behind Julia falling behind C? Well, to start with, it's probably the usual suspect, garbage collection. Another thing that springs to mind is Julia's handling of half-float numbers. Julia does it always in software, or at least it used to. As you are aware, there are SIMD hardware instructions available on Intel and AMD CPUs. Julia can take full advantage of SIMD, but to get the most of the CPU, you still need to call an excellent Intel SPMD-C compiler, otherwise known as ISPC. This brings us to the next claim by Julia Fox about solving the so-called two-language problem. No, Julia does not solve it. It comes very close indeed, but doesn't solve it. So, why would anyone use Julia at all? Well, here's a single reason why the high-performance computing crowd might like Julia. Julia absolutely excels at distributed computing. It beats hands down MPI and CoArrays. It is full asynchronous, and as you can see in this example, it's very much fire and forget. After launching the remote computation, you can do some other things and come back later on to collect the results. It's just so simple and it works. Unfortunately, not everything is great about Julia. There are still some rough edges. Here's a typical use scenario in high-performance computing. OpenMP is used alongside MPI. You use MPI across the cluster and OpenMP within each cluster node. Now you could certainly replicate it in Julia with base threads and the excellent distributed package. It will work fine in many cases, but it doesn't always work. The built-in base threads and distributed.jl simply do not get along very well at present. This might and, well, probably will change in the future. In the meantime, you can always try threads X instead of base threads and, well, see if your problems go away. We have come to the end of the talk. As ever, developers are faced with a familiar trade-off, development time versus execution speed. Handcrafted assembler is the absolute speed demon, but you know how long it takes to code in assembler. Julia's greatest strength lies in fast prototyping, whilst still offering decent execution speeds. And Julia is an undisputed champion when it comes to distributed computing. On the other hand, Julia still suffers from slow startup times. Each time you run your code, it needs to be compiled at runtime. Well, it is just like old petrol cars in the past, which needed a warm-up period in winter. And last of all, on a single server, Rust is not bad at all. So thank you very much for your attention. Any questions?
Thank you very much. And excellent timing as well. So I do believe that we have Christopher joining us through the online platform to ask some live questions. So there is one question that came in through the Discord platform, which is from Angus. I see you have Webgl support with HDR. I've been interested in this in Kata since we could benefit from 10 or 12-bit display output and a wider dynamic range. Was it easy enough to implement HDR, and do you require client-side calibration?
Well, basically, no, there's no client-side calibration. And the HDR part, well, it's handled in JavaScript. So it's handled within the client side, well, on the web browser, but there's no calibration at all. And I guess the Kata viewer uses the Electron framework, correct me if I'm wrong. So the Electron framework might be able to take advantage of the JavaScript, say, HDR capabilities. Well, to be exact, we use Webgl, and as long as the Electron framework can use Webgl, I think Kata should be okay with HDR.
Great, thank you so much. Are there any questions in the room? Okay, I see no questions, so in that case, thank you very much for a very interesting talk.
Thank you for your attention.
Thank you.